All right. So our next use of integrals is to use with inductors. And with inductors, one of the things we know is that voltage is equal to the inductance times the derivative of current with respect to time. So with an inductor, it's similar to a capacitor in derivation, only backwards. Whereas before, capacitors have current is the derivative of voltage. Here, voltage is the derivative of current. And so it works a similar way, only backwards. And we can get to this same idea of an expression where current is 1 over L, which is our capacitance, from 0 to t of voltage with respect to time times I naught. Again, where V is voltage, I is current, and L is inductance. Okay, so when we have inductance, these things work out. And so now for our example, we're going to be given an expression for V of t, and we want to express I of t and sketch it. Okay, so for our example, we want to, again, we're given that voltage is this function which kind of flips back and forth. For the first 2 seconds, it's 9 volts, and then it goes negative 9 volts, and then it's positive 9 volts, and then it's negative 9 volts. So it just keeps flipping back and forth between these two values. And so we want to determine I of t along each one of these and then sketch it. Before we get into that, let's think about, what voltage looks like and what our expression for I of t should look like. So again, if we were to sketch V of t, this is time in seconds, this is V, it's going to be measured in volts. Again, it's just going to bounce between 0, or between 9 and negative 9. And we can guess that there's probably a system in which this just continually happens forever and ever. And that's also one thing you'll see. If you work with oscilloscopes, you can design functions that do this, and they just kind of bounce back and forth. Eventually, we've got the things where you can get these a little more precise, and you end up with something that might look like a sine wave or a cosine wave. Well, one of those expressions, but with rudimentary things, you can just kind of flip them back and forth. All right, and so then the other thing we need to think about is, again, this assumes starting at t equals 0. And that's fine, because that's usually the case. But we need to adjust for a given time. So similar to what we had to do when we had acceleration, going up to velocity, going up to position, instead of evaluating from 0 to t, we just need to evaluate it from t1. So it looks something more like I of t is going to be 1 over L times the integral from t1 to t, v of u du plus I of t1. And again, we just did this because we don't want your math instructor next semester, or whenever you are talking to someone that really actually knows things, to think you're an idiot by integrating from 0 to t dt. You want to integrate on a set of variables and use a different variable for there. So this is just I know in some of the previous examples I worked, I did not adjust that. So again, you can think that I look stupid, but we're going to just adjust the variable there. So that's our new expression. Okay, so now we want to work this out for each part. So let's see how that goes. Okay, so for part A, we end up with V of t is going to be 9 for that first part, between 0 and 2 seconds. The other thing I did not mention earlier is that we do have an inductance given by the problem, which is 500 millihenries, or 0.5 henries. So we're going to use that throughout this expression. And so 1 over 0. So if we use this expression, 1 over L is 1 over 0.5. We're integrating. In this case, we are going from 0 to t because we're starting at 0. Our function is 9. We're going to integrate that. And so we can get I0, which in this case, we would just start out at 0. So it's actually going to be, well, we can go ahead and simplify this first expression. All right, so if we work this out, that simplifies the 2 out front. Antiderivative of positive 9 is 9u. We're evaluating from 0 to t. So we get 9t minus 0. So, and then we've already determined that the initial current is 0. So we just get to 18t for that first expression. And then we know we're going to need this later, so we might as well go and find out that I of 2 equals 18 times 2. So it is 36 volts. Because I'll need that later. All right, so we've got I of t for the part A. Let's move on to part B. So when I'm working on part B, the velocity is, the voltage is negative 9 between 2 and 4. So I'm going to, I is going to be 1 over 0.5. That's 1 over my inductance. Integral from 2 to t, since we start at 2, of negative 9 du plus what I at 2 is. I can know that the integration part is going to be very similar, but let's go ahead and do it. Again, antiderivative is negative 9. Lead coefficient simplifies to 2. I evaluated from 2 to t though, so it'll be a little bit different inside when I plug in values. And I've got 36 for my I2. So if I simplify, so I do the antiderivative, I plug that in. I get t here. I plug in 2 for that. Remember, it's minus. Negative 9 times 2, so it's minus a negative 18. That's going to end up adding 18. Distribute the 2. 2 times 9 is negative 18. 2 times, this becomes plus 36. Oops, that's plus 36 and plus 36. That should just be plus 72. And a good way to check it is, I know that if I plug 2 into this, it has to match up with that one, and it does. And then the other thing I need to know is that I of 4 is going to equal, it's actually going to be negative 18 times 4 plus 72. It actually ends up back at 0. So that kind of makes sense, as we'll see when we sketch it out in a little bit. Okay, so, sorry. Part C, again, voltage back to 9 volts between 4 and 6. So I'm going from 4, my function's 9. I know it's going to start working out the same way here again, that I'm going to end up with 9t in here, minus what I get when I put in, minus that 4 times this, so it's going to be minus 36, plus when I get I4, it's going to be 0. So again, skipping a lot of steps there for the sake of time and paper. But I'm starting to get the hang of this, that whatever this part is, it's just going to be my value here times that's lower limit on the time. So then my actual expression, I of t is 18t minus 72. And I know I'm going to need the endpoint for the next part, so I of 6 is 36. And it's not, again, it's not surprising that my end voltage turns out to be the same end voltage that I got from part A, because essentially I got back down to 0. I apply the 9 volts again. for the same amount of time, it should climb to the same amount of time. Part D just appears like magic. Again, same sort of expression. We're doing from v of t is -9. We're going from 6 to 8. Same expression here. We've got 1/2 going from 6 to t this time of -9. We know it works out to be -9t plus whatever this number is times that negative, or minus whatever that number is times that number. So it's plus 54 this time. Plus I6, which is 36. We simplify the expression. We get -18t plus 144. We check the endpoint. I of 8 is 0, which again makes sense if we know that it went back to 0 on part B, because we've kind of repeated the same thing in terms of what we've done with the voltage. So let's look at what the sketch of this current for this inductor looks like. Okay, so we set up our graph. We know everything stayed in the positive realm, so we can do that just drawing the first quadrant. So we start out, part A, voltage is 9. We know the current starts at 0, and for the first 2 seconds, it has a slope of 9. I'm sorry, for the first 2 seconds, because of the inductance being that, it has a slope of 18, and so it just looks like 18 times t. So it goes from 2 up to 36 during those first 2 seconds. During the second 2 seconds in part B, it has a slope of -18 and comes down. And we know it has to match at that 36, so it's just going to come right back down. So part B is -18t plus 72. It comes all the way down, stops back at 0. Part C has a slope of positive 18 again. The intercept would be -72 if we kept going out all that way. But the main part being that it's going up and again reaches 36. And then part D, again, slope of -18, it comes back down to 0. So yeah, we've got this function that just keeps, it goes up for 2 seconds, comes down for 2 seconds, goes up, which makes sense when that's what we're doing with the voltage. We're storing a voltage, then we're losing voltage, storing a voltage, losing voltage. So this inductor just keeps bouncing back and forth there. Key points we learned on this one is mainly that for an inductor, since voltage is current times the derivative of I with respect to t, we can integrate that to be that I is 1 over L times the antiderivative of the voltage with respect to time, or if we're not doing it from 0, we can use T1 and we have to get the in there. Yeah, and that's really the expression that we learned. Fortunately for us, it was a constant voltage. I mean, it shifted between 2 values, but it was a constant, which made it easy to integrate. You could get a much more complicated function in there, and the integration would still work. It just gets harder as you go.